We're going to talk about the Risk-Averse control, the multi-dimensional Markov process. So we're focusing on the program on state process is final. It is a fully observable system, and we are going to minimize the random distribution, which is the risk-averse Markov method of the. So we are going to minimize the traffic. So our method is to use the policy iteration scheme, which means that we first produce the policy type. First, what we'd like to evaluate. First, we'd like to evaluate the value. Our vector is the top of the count vector and the risk of So remember that our state space is very large. So what we are going to do is that we are going to reduce our dimension into some features, which is only some limited features. We are going to use the linear approximation here, and we approximate the values here by the features with the linear combinations. But we have a problem here, is that on the left-hand side of the equation, that is in the range of all the features, in the linear combination of all the features. But in the right-hand side, it's not always the case. So what we are going to do is just one method we are going to do is that we are going to project the right-hand side into the range 5 here. And we abbreviate that equation to this one. And we are going to solve the fifth point of that equation. So what we're going to do next is that our projection means that under the 200 probability, we found the closest the values in that range, and we found the closest in that range given the Q norm. And we have the distortion coefficients which speaks of the how it differs from the risk neutral method. And we have an assumption that if we have the assumption alpha times the square root of 1 plus kappa is more than 1, we can prove that that equation has a unique solution. So one method to solve that equation, the 6-point equation here, is that we're using the 6-point value here, which means that we fix one theta in the projection equation, and we want to update another one. And step by step, if we have the assumption, we can prove that it is convergent due to the convection property, mapping property. Okay. So far we have known that if we know our policy, we can update our new value, and we need to improve our policy, which means that if we know our value, what is our new policy here? So it's very simple, and it's just a one-step optimization there. And we just find the best feasible controls among all the controls of that. And then we follow the policy improvement iteration schemes, and we can find the approximate values by that structure. So there's one empirical illustration here, which means that we want to solve the robot navigation problem. That is walking around to visit some waypoints and to report the information collected, but we don't want to get the expected value of that control. We want to get the dynamic risk to minimize the dynamic risk of losses. So it's a very high dimensional case, which is about 270 billion states there, but we only want to minimize approximate them in some several selected features, which is like this, like the number of available waypoints, the distance, the shapes, and the distance to the nearest transmission points, something like this. So if we begin from an initialized policy, we can see that we begin from the initialized policy here. We can see that it will behave finally with the risk neutral one and the risk averse one finally behave very clearly close to the optimal policy here. And the values is also efficiently decreasing. So we have our conclusions. The first one is that we have designed a convergent algorithm which solves which uses the feature-based policy evaluation problem to solve the problem. And then it is adventurous to train in the high-dimensional case. And the risk aversion in our cases performs better than the risk neutral ones because it neutralizes the effect of the imperfections of the feature-based models. So that's all for my talk.
Okay, hi. So my name is James. I'm from Carnegie Mellon, and I'm going to be presenting on this ongoing work we have called Convergent Control for Underactuated Hybrid Systems. So the kind of point of this work is, this is a very famous video of sort of legged robots doing these actions where, our first hybrid, where you're making and breaking contact with the ground and experiencing these impulsive forces or these impulses. And then also high degrees of underactuation, where, for example, when you're in the air, you have very limited control over your body, for example. So the research question I'm trying to evaluate here is how to, in some sense, safely control these underactuated systems as they undergo these hybrid events. So I'll spend a reasonable amount of time talking about, what does it mean to be safe or, risk averse in these ways. And the way I'm doing it here is with something called the fundamental solutions matrix. So I'll try to illustrate this with sort of this red trajectory here, starting at some x naught, and comparing it with some perturbed initial condition x bar, right? So let's say we're trying to track this red trajectory, and we start with some initial error, with this green vector. Right, so as we flow through, this sort of example system, right, through our continuous domains, sort of across these dotted lines that represent these hybrid transitions, say like foot touchdown and liftoff, then we eventually, end up at some endpoint in our trajectory at time t, with the red and the blue ending up, at these positions at this time, and we can represent this new error by, say, this orange vector. Right, so this fundamental solutions matrix I'm calling phi, is just a mapping really of the initial error to the final error of this particular perturbed point. Right, and just very generally what we want to do is minimize the size of this final error. Right, and so, one part of our work, if I bring back this initial condition, is how to actually compute this fundamental solutions matrix. And what it turns out is through these continuous domains, the perturbation dynamics basically equate to the nominal dynamics, right? So you have some a minus bk is sort of the evolution of the error through the continuous domains. And the interesting part is trying to sort of map these perturbations across the hybrid events. So we do this with something called the Saltation Matrix Xi here, which does an equivalent thing as sort of the dual across the hybrid events. And so if I sort of play this forward again and have our continuous and our hybrid events as they occur, then what we can do is construct this matrix sort of chaining together the sequence of continuous and hybrid dynamics. So what we're proposing here is incorporating this in sort of an iLQR trajectory optimization framework. So very coarsely, what iLQR does is sort of an exchange of forwards and backwards passes, where in forwards passes, all you're doing really is simulating forward your trajectory with some given feed forward inputs u and some feedback gains k, like LQR gains, right? And you want to sort of evaluate based on some cost function, how the optimality or how good this particular trajectory is. And then during the backwards passes, what you do is starting sort of from the end, you update your feed forward gains and your feedback, so your feed forward inputs and your feedback gains based on a value function propagation, which I'll skip over the details there. So the thing about iLQR is, right, sort of you locally get for free these LQR feedback gains k. The issue here is that the sort of in the continuous domains guaranteed asymptotic stability, but not monotonically, right? So I'm showing here, this is a plot of a classic underactuated cart pull system, in this case, non-hybrid, right? So you can see that while you eventually are able to sort of stabilize your system, you do so where, for example, at around the 2 seconds, this orange plot actually gets worse, right? So if you somehow, had a cart pole that was falling from the sky and hit the ground at 2 seconds, and you're actually very poorly sort of lined up to go into your next domain, right? So this is very disadvantageous for hybrid systems. Right, so what we're proposing here is in the backwards pass, we call this convergent iLQR, where basically we generate sort of this reference trajectory that is going to sort of improve the convergence of the trajectory, right? And so we do this, again, very coarsely with the fundamental solutions matrix that I talked about earlier, where basically we can take these derivatives, and so we can actually follow these gradients and iteratively improve the closed loop convergence of our trajectory to sort of tighten it together to handle the underactuated and the hybridicity of the system. All right, so very quickly, I'll show a sort of elementary result that we have with this sort of slip system where you have this sort of propulsion in the direction that the leg is going in. And what you can see is on the left is just this vanilla iLQR. This bottom is sort of shows that the norm of the fundamental solution matrix says that you have directions that grow in the error, where we can correct that with our convergent iLQR. And these are some plots that show that for final error and also the cost of our feedback effort are significantly improved with this result. So then we're trying to enable, sort of these robots doing dynamic things. This is a step towards that. Thank you.
Now we have Erfaun, who's joining us remotely. Did you ask to unmute? Okay, so I will just. Wait. Okay, can you say something? Can you ask in the chat maybe?
Can you hear me now?
Now, yes. Yes, now we can hear you.
Okay, great. Okay, I guess you can go to the next slide.
Oh, sorry. Okay.
Yes, perfect. So I'm Erfaun Noorani, and this is a collaboration with my lab mate, Christos Mavridis, and our PhD advisor, John Barris, from the University of Maryland at College Park. So I'll be talking about risk-sensitive reinforcement learning, especially exponential criteria, which popped up a few times today. Next slide, please. So the standard RL algorithms are notorious for being brutal and non-robust. And you don't need to go that far to see this. Pick your favorite example. I took cart pull, which is an inverted pendulum on a cart that you're supposed to push the cart left and right and balance the pole. And train it with your, in this case, actor critic, but you can take your favorite algorithm and train it to perfection. Now, at the time of test, change one of the parameters of the environment. I changed the length of the pole, and you see a big performance degradation. In some cases, it goes almost to random policy. And it's non-linear, so a slight less change in the parameter of the environment could cause significant performance degradation. And that's exactly because we're just taking care of uncertainty with expectation. Next slide, please. But from the control literature and Markov decision processes, we know that risk-sensitive exponential or entropic risk measure has robust properties, and it has been explored in the control literature for general nonlinear systems, and it has been the equivalence to robust controllers has been shown. So we know that this has some robust properties. And if you develop an actor-critic algorithm, which is precisely what we did, you would expect to see more robust performance. And if you look at the figure on the right, you will see that the red and green curve, which are the performance of the risk-sensitive algorithm for different betas, positive and negative, is consistently near 200 for any length of pole, but the risk-neutral one degrades. And we extended this to also reinforce algorithm, which is a Monte Carlo algorithm. The same results hold there. Could you go to the next one? So it is important to use risk-sensitive algorithms. It gives you robustness and generalizability, which is essential if you want to do the training in the simulation and then extend your algorithm to real-world scenarios. Could you go to the next one? So, but the question is, why exponential? Okay, exponential is mathematically appealing. It has been explored in the literature. It has robust properties, but there are a host of them, and they popped up a few times. CVAR, mean variance, VAR, and the list goes on and on. And the question is, how can we systematize the knowledge and see what risk measure is better than the other? There has been some systematic approaches to categorizing risk measures in the financial literature, specifically the coherent and convex risk measures. But the question is, would those assumptions and those axioms extend to the robotics and control tasks? So this is something that I've been thinking about, and I hope you guys can help me to get to some conclusion. To conclude, robustness is essential. We developed some risk-sensitive algorithms that have robust properties, and also this is not the only benefit of going risk-sensitive. You get better sample efficiency and better performance as well. And that's it for me.
Yeah, wonderful talks. Thank you, everyone. This is a question for the first speaker. So I'm wondering if in your work you have also proved that the fixed point value function is continuous, so that the linear combination of polynomials is well justified.
Yes, it's convergent.
No,
I mean,
continuous.
the-
Like VI pi.
yeah, it's continuous.
It is continuous.
Yeah, it is.
Which paper did you guys do that in?
Oh, we just submitted, but we haven't get the. We just submitted at the end of this March, but we haven't get any return in any.
Okay.
Yeah.
Yeah, I'll look up your paper. Thank you.
Okay, thank you.
Thank you. I'm trying to figure that out, so it's helpful.
Okay.
Thank you.
Yeah, so for the third speaker, what is the difference between the beta negative and positive in the, it was a few slides back.
Yeah.
Yes.
The
In the
sign
last-
of the sign of beta determines if you're risk averse or risk seeking. So if you can think of like the cost distribution, if your beta is positive, meaning that positive is, I think, risk averse. Yeah, positive is let's say positive is risk averse and negative is risk seeking. Then it, depending on your risk attitude, you're optimizing either the right tail or the left tail of your distribution. I hope that answered your question. Okay, great.
Any other question? No.
I have a question for James. Do you assume that, can you maybe go back a little bit to the where he shows transitions between these hybrid modes a little bit more? little bit more. Yep. So do you assume any uncertainty on the hybrid transitions you have, or do you just say, I really have a model, I know everything about it, and now I'm just gonna deal with the uncertainty in my trajectory convergence?
Yeah, so it's interesting. So really, yeah, we're not assuming any uncertainty in hybrid events. So you specify, like where you assume your ground height is, and or stuff like that, for example. Sort of the one thing we're thinking about, sort of extending this work is, in an MPC sense, if you contacted the ground early or late or in some different configuration that you're expecting, and you sort of came out of it, differently, then you can sort of sense that something must have happened, some perturbation that occurred, and to try and correct with that with something like this to bring me back, quickly and through these hybrid events, to converge back to my trajectory.
All right, thanks a lot.
We have the lunch break now, and Bilal has some announcements for lunch, right?